In this video, we discuss advection equation with the variable coefficient. It means that we are going to write advection equation like this. And this f, which is a flux function in this scenario can be written as u, which is a function of x and the value q. If you remember that from advection equation for constant coefficient, we had partial q by partial t, partial by partial x, f of q is equal to 0, where the flux function is u bar q, and this equation becomes u bar is constant, which is speed of the object, which is speed of the tracer, which is speed of the q, which can be density. So this becomes u bar partial q by partial x is equal to 0. So in this case, for variable coefficient, we define flux function where this u is no more a constant, but it depends on x. We put this value into above equation 1, partial q by partial t, partial by partial x, u of x q is equal to 0. Now the question we ask is whether the characteristics for this advection equations are linear. And another question we can ask, either this q is constant along the characteristics like it was for advection equation. In advection equation, we saw that dx by dt, the characteristics were x minus u bar t is equal to constant c. And this constant, if this constant is x naught, then x is equal to x naught plus u bar t. And the dx by dt, if we just differentiate dx by dt is equal to u bar. So the characteristics you can get from this equation. Another thing that we saw in our previous video was that dq by dt was equal to 0 when q is along, should write along x minus u bar t is equal to x naught. So it means that q is constant along characteristics. Okay, so this was what we did previously. Now I raise it. Maybe I don't raise it, so I can take a reference of that. Now we do the same. We try to understand what will happen if we have a variable velocity. Suppose we follow the same pattern, dx by dt, as we did for advection equation, dx by dt is equal to u of x. And if this is u of x, then we also have, for example, dq by dt is equal to partial q by partial t plus partial q by partial x dx by dt. During the advection equation, we had this connection over there, and we apply the same x minus whatever that is. We don't want to write it over here. Now, you can see that partial q by partial t plus dx by dt is u, which is a function of x, partial q by partial x. Now I raise that. We already review it. Okay. So this is not equal to 0. Let me just prove that how this is not equal to 0. For example, we have partial by partial x, q, and u. This becomes partial q by partial x, u as it is, plus partial u by partial x, q. So this quantity, which is also appear over here, we take this value, we put this value over here. Let me just write it. Partial by partial x, q, u of x is equal minus partial u by partial x, q, partial q by partial x, u of x. We put this value into this equation. We get dq by dt partial q by partial t plus partial q u of x divided by partial x minus q partial u by partial x. Now you can see that this quantity is the same as equation 1 with this flux function f. So this quantity is equal to 0 minus q partial u by partial x. Now we can see that dq by dt is not equal to 0. It can only be equal to 0 when q is equal to 0, which is not possible. So we can say that q is not constant on characteristics. And we will see what will be the characteristics. We get the characteristics from here, from this equation. Remember that whenever you are asked to find the characteristics, then you should use this equation. Now here, we conclude that q is not constant. Q is not a constant on the characteristics. If it is not constant, it means that q does not give us, q travels on the characteristic, but q does not give us a straight lines. Since this video is a bit longer, I'll give you a concrete example on this topic in the next video. Thank you for watching.